Hey everyone. So today we'll be talking about RAG in the context of large language models. So RAG stands for Retrieval Augmented Generation, and it's a relatively novel technique within this space. And its main idea is that it allows users of large language models to enrich these models. So more specifically, to enrich the prompts that are sent to these models with very specific data. In this case, data that comes out of a specific type of database called a vector database, which is essentially, it can be any type of document, so your own documents, PDFs, markdowns, text files, even HTML files, anything you can think of. And the idea is that we will use what is called an embedding model on top of these documents in order to generate vector embeddings, as it's written here. So just a quick side note, this is the Llama website. So Llama is a really cool project that allows you to run open source large language models locally on your own hardware. It's really cool. You should definitely check it out. Indeed, so embedding models, vector embeddings. What is this about? So very simply, the idea is that in order to actually effectively do this so-called retrieval augmented generation, what happens is that we can simply take a PDF and just feed it to a model and hope that it will just read through it and choose whatever it is that needs from it. It's at a high level, that is how it works, but under the hood it's a little bit more complicated than that. And the reason for that is that we basically need these embeddings in order to be able to do effective searches on these documents, and also in order to make sure that we retrieve the right context based on the queries that we send to this model. That is how it's all set up. So as you can see here, at a very simple high level, we just have plain text. So Llama, the easiest way to get up, etc. here. And we use an embedding model, which is a model that was trained to generate these vector embeddings, which are essentially what you see here on the right side. So it's these long arrays of floating point numbers that attempt to encode some meaning of this text. So what this means is that based on the structure of this sentence, on the words that are there, the order, the dialect, so the language itself, it's English, etc., a bit technical. And what this means is that these floating point numbers on the right, this large vector, somehow tries to capture the meaning that is in this sentence based on this vector on the right. And the whole idea of RAG and why it works so well is that then we can actually store these vectors in a database. So it will not be your regular relational database. It's a specialized database. In this case, it's what's called a vector database. And the idea then is that we can perform standard similarity operations like we would do on vectors, right? So two vectors are considered similar, if they have, things like the same direction, the same magnitude, etc. And the angle between the vectors will also be an important part of determining the similarity. And then somehow what happens, and this is like the magic of this whole thing, is that if you get similar vectors, if you get similar embeddings, it probably means that the text itself, so what was embedded, is also quite similar in meaning, right? So that's the whole point. And Llama, so this is what we'll be using because let's say it's all open source, it's all easy to set up with Docker and locally, it's very simple. And Llama offers three different embedding models. This MXBAI embed large, the nomic embed text, and this mini LM. So they have different sizes. We will be using the large one. So yeah, just because with these type of things, typically it's like the idea is that the bigger the size, the better the performance in a way. And this MXBAI embed large, it's from this mixed breed AI company. So it's yeah, it's a very nice embedding model. It seems to work pretty okay in the tests I've done. So strong, powerful, and large. So it's nice. And the most important thing to know is that this embedding model has 1024 dimensions. So the dimensions, it's something very important, right? So typically you would look at a vector in a 2D plane, so to represent, I don't know, some velocity, for example, on an XY Cartesian plane. It would be a two-dimensional vector, right? So two values. And these vectors, they have much more dimensions. In this case, the vectors resulting of applying this embedding model, they have a size of 1024. There are larger ones, there are smaller ones. It also depends on the use case, but this is what we'll be using today. And then let's move on a little bit to the rest of the stack. So we will be using an extension for Postgres called PGVector. So PGVector, they basically stay in the name. It's an open source vector similarity search for Postgres database. So the idea is that with this extension, we can store vectors in a Postgres database and then perform perform a lot of similarity searches on it with different types of let's say metrics, right? So we can use the cosine distance, we can use this L1 distance, we can use L2 distance, and we can use inner product. So the inner product of the vectors, it's related to what I mentioned earlier about vectors being closer together, the angle between them, etc., the dimensions. So it's all related like this. And yeah, this is the basic idea. And then of course we will be using Spring AI. So Spring AI, it's of course it's a very recent library to support Springboot and Java developers to leverage these large language models. And they also provide an embeddings API, which is what we'll be using today. So yeah, this is at a very high level. This is the diagram here. They also have the interface here that we can leverage. So we can embed documents. We can embed multiple batch of text, so multiple documents into multiple vectors, etc. So then we can perform embedding requests, get embeddings back, etc. So this is all very straightforward. And as you can see, and this is also interesting for us, is that there are quite a lot of implementations here that we can use. We will be using these Llama embeddings today. The idea, of course, is that we will be using Llama3 because it's open source, easy to understand, easy to tweak, and this is what we'll be looking at today. So let's move on to the code then. So here is the code at a very high level. Of course, first we'll look at the Docker Compose file. So all of this starts in a completely self-contained way with one single command. So Docker Compose up, it all just goes from there. And yeah, the most important thing is all these environment variables that we needed to configure for making sure that we can have a local Postgres database with the PGVector extension installed. working with our large language model, right? So here is what we need. So we have a URL for the database. So this regdb, as you can see, it's defined here below. So this will be the database. We are using the PGVector Docker image. We give it a name. We also use an init script that I can quickly show here. So very simple. What it does is that it installs all these vector and store extensions that are needed. It creates a vector store table. And of course here the most important thing here is that by default PGVector embedding size is 1536, but we need this init SQL file, so we need to inject ourselves in between this bootstrapping process, because we need to have 1024 as the vector embedding size in our vector database. Why? Because the open source embeddings we are using from XB AI embed large, so this one here, it has 1024 dimensions. So this is really important, and this needs to match, otherwise things won't work. And finally, we create an index. We will look shortly after the demo at what these indexes are, how they work, what different types are there, and yeah, this is basically it. So what happens is that we have a setup Docker image using Llama, of course, sharing a volume with the actual LLM here that pulls the embedding model, pulls the LLM itself, starts it all up. This is, of course, just to be able to do everything self-contained. It would be much better to run Llama directly on top of your own hardware. For example, if you have a MacBook, that would go significantly faster, but we don't, so that's what we'll use. And then indeed, yeah, we set up all of these. Also quite important is this environment variable here, remove existing vector store true. We need this because, yeah, by default, yeah, this embeddings API and this PGVector, it would create a vector store table as well, the same name, but it would use the wrong embedding size, 1536, and then it wouldn't work end to end, right? So yeah, that needs to be tweaked. We have a very basic front end as well, an Nginx image that depends on the backend. And let's just now see it in action. So we see also that the Llama model downloaded, got pulled, the app started. So now it essentially means if we go to localhost here, this is the UI that we have. So we can upload our own files and chat with the model. So let's see. We will upload, we'll upload this PDF. This is just a training plan for running the 5K. We will ask it some questions about this document, and we'll see how well it fares against it, basically. So let's go ahead. We will actually choose to upload this PDF. We press upload. Then we see, we can see here that, yeah, we hit the front end. We are now uploading. The this document. Maybe not. Let me double check here. Okay, upload. Yes, now we are uploading it. So we can see that we are uploading it. Why? Because the Llama LLM, so the embeddings are being generated, and we see, of course, that yeah, the embeddings model kicks in to start embedding all the content in this document as text. Of course, it takes a while, um, but it's doing it. So okay, stored here. So we see that we stored the embedding. So let's go back here, we refresh, we see that we now have our document here, right? And now here comes the magic. So let's open the document one more time. And so, for example, we see that we have this building base endurance title on these weeks 1 to 4. That is something we might want to ask the model about to see if it finds it out, or we do long runs on Sundays mostly. So only Sundays the long runs happen in this training plan, which of course, yeah, it's nice. So maybe let's ask about that, right? So let's ask when, on which day of the week are long runs done in this plan? So on which day of the week do we do long runs according to the training plan? Now we can send this, right? So we see now that this is quite nice, right? Because this question, so if we would ask this question just as we did now to ChatGPT, it wouldn't know, right? Because you know, it would think, what training plan, or what are long runs, or what are you talking about, in a way, right? Because this would be information that is not available by itself. So the context in which this information is available is not really very simple for an LLM to follow. But with retrieval augmented generation, this is what we can do, right? So we have uploaded our document, a PDF containing data that we want to query the LLM with, and we can actually, you know, we can know about it, and we'll see that the LLM will probably give a nice answer to it. So again, it's a little bit slow because of course this is running on the CPU only. But yeah, as you can see, we now are running the Llama3 model. Also, interesting enough, we see here that the question that we sent to the model in our prompt, so let me quickly go back here to the service. So we have a context and we have our question, right? And then we ask the model to generate an answer. So the question is what we sent in the UI, on which day of the week do we do long runs? And the interesting thing is that with retrieval augmented generation, this similarity search, so we would just retrieve the first document because, yeah, there's only one for now. But we see that it could figure it out, right? It could retrieve the related document about running and use this as an additional context to this question, which means that the model will probably know that, okay, we need to do long runs on Sundays. Okay, now we see that it replied correctly, so we have our answer now. So let's go back. And here we are. According to the training plan, long runs are done on Sundays. This is perfect, right? This is exactly what we needed. And this is something that the model wouldn't be able to know without referencing the uploaded document. So this is really powerful. And yeah, this was just a small demo on how a RAG pipeline could work locally. It's quite nice. It also makes it quite easy for Spring AI and Springboot to configure this. So the idea is that we have an embedding service that receives as input a document that we upload. It converts it into a document, it embeds it, and then it stores it in the vector store. So this vector store, of course, it will auto-wire a bean automatically. In this case, it will be the Llama vector store, because we have in our Docker Compose the Llama embedding options here, so it will know and the base URL, so it will know how to use the Llama embeddings. And yeah, this is basically it. Just as a final remark, the index type, this HNSW, it stands for Hierarchical Navigable Subworlds. It's quite a mouthful. But there is this really nice post, Avon.io, about vector PGVector indexes, and it's quite nice. It really explains what vector similarity is, which is what we discussed at a high level. It explains what embeddings are, how to understand these vector queries, and then it goes into quite some level of detail about the different types of indexes and similarities, and it's quite nice, right? So you can go over it. It's a really interesting read, quite nice. Gives a really nice intuition on how these embeddings are built, and yeah, it works really well. Out of the box, it's a really nice blog post as well. And yeah, this was it. I hope you enjoyed this short tutorial, and yeah, keep on coding.